All right, so I posted homework too, so everyone has access to homework too. Also, I posted a set of practice problem for transfer functions, just to give you extra practice problem for getting ready for exam, or to feel more comfortable if you learn those or not. You should use your book. How many of you actually are using the book? Just put in the chat like yay or nay. Who is using the book? A little, no, nay, a little, nay. Okay. Yeah, everyone just answer. So I know it's not a robot. All right, yeah, we had a case of student putting robots in Zoom classes when everything was on Zoom. Okay, so your book has good examples, and right now we covered chapter 1, 2, and 3. There are some sections that I might not have gone through, especially for state space, because I'm waiting for today's lecture to be done, so you're familiar with mechanical and electrical systems. So when we combine them and then we go from transfer function to state space, it will kind of make sense to you. All right. So definitely look at your book, look at the examples. If especially you are not confident in one of the topics, your book has a lot of examples that you can solve, and you can play around, change something on the example, try to solve it. If you couldn't solve, come to me or Brett. So part of learning for you is practicing. I can't do anything for that. I can teach you, right? And I can go through the book examples and explain those to you, but I cannot do the learning part for you. So you have to do that part yourself. So I trust that you will use the book, you will use the practice problem of the book, you review the lectures, and also the set of practice problem I gave you. It is also a good way of practicing if you don't have time to go through everything in the book. Now, what else did I do on Carmen? CP6 is published. Force analogy that I will talk about it today. There is a page I added that there's 2 videos in it, and those are very useful when if you didn't understand everything fully today after class. Those are good videos to watch and to help you with the assignments. Now, I actually don't know what am I recording, because I have 3 monitors here, so hopefully I'm just recording my iPad once I'm writing. Let me do the full screen again. All right. So today we will talk about electromechanical analogous systems. So meaning that we talked about on Wednesday briefly that if you have a mechanical system, you have an electrical system, you saw that some of the equation looks the same. And through a process, we can use one of the systems that we are more familiar with, convert a system that you're not familiar with to it, and use the same equation. Now, for electrical system modeling, you use either Kirchhoff current law or voltage law. You're all familiar with that. We did a couple of examples. You can use nodal analysis, mesh analysis, and solve the circuit, get all those equations, right? And then from there, you can either convert the equations to state space, which we'll practice more, or convert it to transfer function that we have done some practice and you should be comfortable with. Now, for today's lecture, how much you should actually spend time in analogies and analogous system? I would say not very much time, because at the end of the day, you will be dealing with mostly electrical networks. So mechanical system might not be what you will deal most of the time, but you need to be aware of those equations as well, because it might show up in your project and you need to have an understanding. So I dedicated 1 lecture to this, but the weight of the material compared to the rest of the course is not as much, but it's good to know for you what these analogies are, what are the 2 analogous systems. So 2 systems are said to be analogous to each other if they follow 2 conditions. 1, these 2 systems are physically different. So one, for example, is a mechanical system, one is electrical system, right? but their differential equations are the same. So does that make sense? So you will have, no, it doesn't make sense. So let's say mass spring system and RCL circuit. We have solved both of them. And if you remember, they both gave us a second order differential equation, right? Their coefficients were different, but similar type of equation. We say that their governing equation are the same, but these two physically are two different systems. We call them analogous. And I will show you that the response of both systems will look the same because their governing equation are the same. They're both a second order differential equation, for example. Now, for electrical system and mechanical system, we typically use two type of analogies. One is called force voltage analogy. So force from the mechanical system, voltage from the electrical, meaning that we can find relation between force and voltage. Or we can use force current analogy. So again, force is from the mechanical system and current is from the electrical. As you can see, the input to a mechanical system is always force, right? Or torque in that matter, if it is a rotational motion. But in electrical network, you could have voltage. Voltage might be your input or current might be your input. That's why we have two kind of analogies. Now, these next four slides are important. You kind of want to go back to them when you are, if you want to use the analogies. So force voltage analogy says that the two model that you see on the right. So this one is a mechanical system. This is an electrical system, right? These two are analogous. If you derive their equation, they will be similar. Now, we could, if we had, let's say you have this mechanical system and you're not very comfortable or confident of writing their equation. If you could convert this to an electrical network, electrical system, then you will say that I'm very comfortable writing the equation and analyze it. You can do that if you convert them properly using this table, right? So this, I'm going to show you 4 pages. All 4 kind of are the same. So here we have force voltage analogy. This is important. Now, if you see in translational mechanical system, force, which is our input, usually, well, most of the time, our input is in form of force in a translational mechanical system, is equivalent to voltage in electrical system as an input, right? Sometimes you have a battery as voltage source. So if you have a translational mechanical system, you want to use force voltage analogy, your input force is equal to a voltage source. Then these are your components, right? So mass, frictional coefficient, could be a damper, could be a friction, and a spring constant K. So these 3 are equivalent to these components in electrical system. Mass is an inductance, frictional coefficient is resistance, so you can give the value of B to be R and model it with a resistor and it would be the same thing, right? And your spring constant K is 1/C and is a capacitor. So you have 1-to-1 relation. You have for each element in mechanical system, you will have 1 in electrical system, and you'll say, for example, M equal to L. So now if you were in mechanical, you say it's M. If you were in mechanical, M, in electrical, L. So here K would be 1/C, for example, and B will be R. So when you are using one system equation to convert to another, you can easily do that. Then your displacement usually something that you're looking for. So either is X or Y or Z, whatever we call it, will be charge Q in electrical system. Velocity here, the output, let's say either of these are your output, right? Either you could have displacement as your output or your velocity as your output. So it's X dot, Y dot, Z dot, right? That's the only 2 things that we could have as output in our mechanical system for second order systems. Then in the equivalent system, you will have the current as output. So these are your output. Now, if you were given the displacement on him, like for example here, this is displacement. When we convert it to electrical system, we know that this has to be electric charge. So I will show you a procedure how to do this, but it is important to remember what from mechanical system is equal in electrical system. Now, this is the force voltage analogy. If you are in force voltage analogy, the mechanical equation are compared to mesh equation of electrical system. You see that you can create a series component and say it is equal to that mechanical. Now, if you have rotational motion in mechanical system, you use torque voltage analogy. So torque as input becomes voltage as input because we are still in voltage analogy. So the right side, the electrical system remains the same, but for the mechanical system, because it's rotational, you have torque, moment of inertia, rotational friction, torsional spring, angular displacement, theta, and angular velocity, omega, which is theta dot. Okay, so these are your output. So this is just to convert it to a different system, to different thing. I just saw someone's question. I'll answer your question once I'm done with this. All right, and then these will be the output on the electrical side. We have another analogy. The second one is force current. So you see that force is for translational mechanical system, and then we have current. Sometimes we are looking to find, we are using current as our state, or as basically as our input to our, so this is input to mechanical, input ME, this is input of EE, electrical, well, not engineering, electrical system, right? So now force here, the input becomes current source, right? So this is the input. So if we want to use force current analogy, if we saw a force, we need to translate it to a source, to current source, right? So this is the same mechanical system. We can use two different analogy and write two different circuit for it. We just need to say what analogy we use, convert it properly, and then we will have a set of equation. Then these are the components, which you see that these are electrical component, but now there is a difference here. M is going to be a C, B, your frictional coefficient is 1/R, and spring K is 1/L. So now your storing will become 1/inductance. Then your displacement X and V, so which V is X dot, so X and X dot are your magnetic flux and voltage. So if one of these two output is something you're looking for, you can use force current analogy. Usually we use nodal for this, all right? So you see this is a big node, remember supernode? So this whole thing is a node. I can write nodal. I can say, for example, if this was I1, I2, I3, I can say I is equal I1, I2 plus I3. If you solve this, get the differential equation, and you solve this, get the differential equation, they will both be similar form. And then for torque current analogy, the only difference here is torque is the input because it's a rotational mechanical system. The right side, the electrical system is the same. Your input is torque instead of force, and these are the components, and your output is theta and theta dot, which are angular displacement and angular velocity. So same thing. So you have to be careful what kind of analogy you're using. So if you have a rotational motion, obviously torque current or torque voltage. If you have translational mechanical system, then it's force current or force voltage. Either way is correct depending on what output you're trying to find, all right? So if you remember in here, current was the output, so we use voltage analogy. If voltage is our output, something that we're trying to find, we use current analogy, so the other one of them. Now, Osama is asking that, do you have any intuition explanation why is mass becomes inductance? So you saw that mass is not always inductance, depending on what analogy we use. I would say component that they are restoring energy. They are kind of the same in both, and then related to inertia. But if you pay attention, in both cases, friction is becoming resistance, right? Because it wastes energy in both of them, so it's resisting. Now for sometime your mass becomes a capacitor, sometimes because it becomes inductor, and both of them restore energy, but I don't know exactly why we are doing one versus the other. I can look it up for that one. Interesting question. I didn't think about that. But try to follow this table whenever you are trying to do the analogy, and make sure that first you understand what system you're converting, and then what analogy you're using. The analogy usage comes from basically what the state you're trying to control or find, right? Let's solve an example to kind of work this out. Any question up to here before I continue? All right, so hopefully you will be able to write the equation for both of these. I'm going to quickly write the equation of motion for both. For mechanical system, and this is a translational motion, right? Translational. So these are the steps. Identify what kind of motion you have, translational, drive free body diagram. So I will always identify the mass. I identify the displacement. If it's given to me, I place it. If it's not, I identify one. Then I identify the force, which is our input, right? So in mechanical system, we know that force is our input. Now here, again, I'm going to eliminate and not consider the gravity. I would assume that this was stretched and then the force R was used. But if we have to consider gravity, if it was like real zero, we will say this is mg. This is just another force. They're both our input. So your input actually becomes RT plus mg. This doesn't depend on time, so it's just a fixed number, right? You just carry over. That's why a lot of time, if you just pulling down, you're not studying the fluctuation, go back and up, back and down, you can eliminate, or even that, you can completely eliminate it because it's a fixed number and we have superposition, right? We can just separate these two, separate RT from mg effect. This is our LTI system, so we can consider these two separate. Because some of you asked question, and that's why. So I'm going to not consider the gravity here. All right, now the force is pointing down, the direction of y is going down, so this just means that the system is supposed to be going down. Now ky here wants to resist up, and you see that there is a wall friction. We will model this as like a dashboard, like it's a friction. We will model this as by dot, because friction wants to resist velocity, right? So I don't even go and look at the table I had for forces. I'm just basically trying to understand what each of these components are resisting, and I'm putting their force. That's the best way of learning, because you're not relying on memory, you're relying on concepts to understand what is what. Now there's one force missing. What's that force? Connor?
Inertia.
Oh, yes, inertia. So inertia also wants to resist the motion, right? So inertia will look like this as well, my double dot. Now I identified all of the forces. Again, this is all repeat, but I think the more I repeat, the easier it becomes for you, especially when you have multiple mass. Every time multi-mass system, identify all the masses, you have to draw free body diagram for all of them. And that's the process. So sigma F equal to 0, or can say sigma F equal to my double dot. Here, negative my double dot, because it's in the opposite direction of my displacement. negative by dot, negative ky, positive plus RT because it is in the direction of the displacement. Now, if I put them, if I organize them, plus ky equal to RT. So this is a second order differential equation, right? So, or ODE, second order ODE, differential equation. So this is when we talk about type of or governing equations. So this is a second order ODE. Now, if I write the equation for the other circuit, if these two are analogous, I have to find the same form, right? So now here, the input is R. R is the current. So here, the input is current, right? So this is a forced current. I can use a forced current analogy, but I'm just going to cheat a little bit here. Since I have displacement on the mechanical system, I know to get the same equation. So this is just a little cheat sheet, but now I'm going to just do that. So I'm going to use nodal analysis. So if you remember, for nodal, you first give a ground, and then I can say this is whole one node. This is I1, I2, just going to say I3, just for make it easy for myself. And this is your RT because this is the current source, right? That wasn't simple. So I can say I1 plus I2 plus I3 is RT. I wrote I's lowercase, so I know this is just a function of time. And now I across resistor, I just write, you have to I across resistor, inductor, and capacitor. So VT over R plus 1L integral of VT dt plus C dVT dt. So these are all equations for each of the components. This is equal to R of t. So I know that I want to write this based on flux because my goal is to show you these two are analogous. So I'm going to sub VT with the flux T dt. So this is magnetic flux. So if I replace all the VTs with this, I will get 1 over R d psi dt. So I'm going to eliminate T here. It's just faster to write, but don't forget it exists. 1 over L, this is psi, not putting T, plus C e psi e2 psi dt2 equal to R of t. So now if I reorganize and write it in like with dots and double dots, so this is C psi double dot plus 1 over R psi dot plus 1 over L is RT. Okay, so this is also a second order ODE. So both of them have the same governing equation. Now from here, C is M, right? That, so you ask, where do they come from? 1 over R is B, and then 1 over L is K. So these are already in that table. So all of these have been done for you. So if you say that, hey, I want to use force current analogy because, well, force voltage analogy because my source is current source, then go to that table, replace the items, write the equation. Literally the same equation, you just change the values here. A lot of time I will ask you, if I give you, I ask you to draw this. That's just a good practice to see how they will align. I will show you a visual way of doing it. But in general, what I want you to look at right now is this equation and this equation, right? You see their input, but input is input. They are the same kind of equation, only difference is the coefficients. And we found a relationship for the coefficient. So mechanical system is a mass. Based on this analogy, mass, you can convert it to capacitance. They're doing the same thing. All right. Now, if you plot both of these, you will get similar responses. Now for mass spring system, so my double dot plus by dot plus ky equal to r of t, rt, sorry, you get this response. So this is your response if you have underdamped case, and if you have overdamped, you get the green one. Now, if you draw typical response or response for RLC with the same thing that we saw over here, you will get the same response. So these are two systems that physically are different because one has massive spring damper, the other one has RLC, but so two different physically, but similar governing equation, then we will expect the response, time response to be the same. That's why we say these two systems are similar. We can say they are analogous. Does that make sense? Now, how much I want you to go in detail, I'm not going to give you a very complicated circuit. The idea is just to understand if you had a mechanical system and you wanted to know what kind of equation you would have, you could write an analogous electrical network and kind of guess, because as electrical engineer, you are more prone to deal with electrical network and you kind of know most of the equation by heart or you have in your textbook, but you don't have maybe access or practice on mechanical system, right? So this is kind of like more of information, useful information for you, hopefully. And so Kevin says, in this example, does the capacitance correspond to mass because of the current source? So yes, so if we go back here, because we use so we had current source, right? I'm gonna make this. In our example, we had current source in the electrical system, and our mechanical was a translational mechanical system. So we are in this case. Our case is force current analogy. So if you look here, if you have a mass, it will be converted to capacitance. So as you either use this table or you use the equations, both of them are the same. And Brett actually answered, I thought another question, another student that said, yes, I understood. So thank you, Brett. But yes, so these tables become more important if you want to understand the relation between electrical and mechanical system. Because when you're dealing about control, really doesn't matter, like you have to have understanding on both of them. How do they work, right? Now, what I have for you is visual method for force current analogy only. This is only for force current analogy. Force voltage is the same. You just have to go to the table and adjust these steps based on that. So for force current analogy, if you have electrical system and you want to draw mechanical without doing any of the calculation, without actually writing the equation, here is a good visual way to do so. So you start with electrical circuit, label all node voltages. So this is 1 node, 2 node, 3 node, name them V1, V2, V3, right? And this is your ground. So just know that you have also ground. So voltage for ground is 0, right? And so if you have a voltage 0 and it's ground, in mechanical, they also have a ground that does have 0 displacement. So it's kind of the same thing. So V1, V2, V3. Then if you have a current source, replace it by force generator. So here we have a current source, right? I can start and say this current source becomes, this is like force, right? We show force usually by an arrow. Then if you have a voltage source, you can say it's an input velocities, right? Then convert all resistor with friction elements. So friction is dashpot. You can show dashpot like that. It could be friction or just like, if you do this, it means that it's, the equation is dV dot. All the inductor with a spring and all the capacitor by mass, but make sure that capacitors are grounded. Again, here we are only doing force current, right? So we know capacitor is equal to M. Now, draw on top of your electrical circuit. So here is force. Here I have a resistor, I'm going to draw a dash plot on top of it. Then this is my other node, right? So they're kind of then connected to inductor. I'm going to draw a resistor. Then I have a resistor. Here is a dash plot. I have a capacitor is a mass. So this is a mass. And then this mass, so here you have this current grounded. So, sorry, dashboard grounded. So here is the ground for mechanical system. Now, each node from the electrical, from like, so your V1, V2, V3 becomes X1, X2, X3. Why this is important? Because these are the states, right? Because you're trying to find V1, V2, V3, if you remember the state vector. Now, your state vector is X1, X2, X3. So you're just everything is being translated just in a different system. It just shows differently. Does that make sense? So this is how you go from electrical to mechanical system. I didn't do any equation. I didn't write any equation. Just use visual methods. For going from a mechanical to electrical from visual method, again, here the example is force voltage. You can use kind of similar method. Label all the positions. So here, position X1, X2. So we know we have two states, right? So we expect to have two states in our electrical system. We are going to draw over our circuit on top of this and replace all the mechanical system with their counterpart for force voltage analogy. So that means if you have resistor becomes inductor, sorry, this is the spring, becomes inductor, your mass becomes a capacitor, has to be grounded. You see the ground here. Then you have another spring that becomes inductor. You have a dashpot or a friction element becomes resistor because that one we know is wasting energy. And then you have mass, another mass. So this mass is also becomes capacitor. So you see that here, this M2G, well, this is there is no force, it's just a gravity. And we can show that as a current source. There you see another current source here, and that's the M1G here. So in this example, they assumed gravity, so it counts for both of the masses. That's why you have two current source. Now, if you bring out your circuit, this is the equivalent circuit to this, and their governing equation will be the same. Now, tell me how many sets of equation you will have and what kind of equation they are. You should know one of these two systems, and it works for both of them.
Professor, did you mean force current for this one as well?
Yes, sorry, it's a force voltage. I'm sorry, force current. Both of these are the same, force current. So basically, I use the table that I introduced earlier for two different systems, right? Thank you. So force current, and then so tell me how many sets of equation you will have and what's type of equations. Anyone wants to volunteer? Two systems, so two sets of equations, right? And then what kind of equation do you expect? Like what kind? Are you gonna have differential equation? Are you gonna have the first order differential equation, third order differential equation? So remember, one mass system had one second order differential equation. Now, if you have another mass system, you're gonna have another set of this. So I know even without doing this, I'm gonna get two sets of equation. Let's say ax double dot 1 plus bx dot 1 plus cx1. I don't know what these are, but some input, right? And then I'm gonna have a prime x double dot 2 plus b prime x dot 2 plus c prime x to some input, some other input prime, right? So these are things that you should be able to observe when you're dealing with systems, either mechanical or electrical. So how do I know with the electrical system? Well, you have two capacitors, you have two inductors. You know that these are, do you remember how to identify the degree, like the order of your the differential equation for your electrical system? If they're first order or second order?
The amount of components.
We look at the components that restore energy, right? So the resistor is not important, basically. So if you have one capacitor, becomes first order. If you have a capacitor and inductor, becomes second order, which is this case, right? So you will have two second order equation in this electrical as well. So these are the things that I would expect you at least to know after these 4 weeks that we had together, by looking at a system, being able to say how many set of equation you have, what kind of equation they are, and hopefully from now you would be also able to say, or at least estimate, what would be their analogous electrical or mechanical system. All right, again, don't put too much time on this, but understand the concept and solve a few examples so you'll have a better understanding. If you go to this link that I put here, I grabbed this example from this link because I thought they said it the best way. They have some extra information. So if you click in there, you'll see it. Also, the page that I mentioned, the two videos are very informative. And if some of you wanted to get you can watch those videos. Now, for today, what time is it? 3:39. So this is your class participation. You can either do it now in class and be done with it, or do it by the time is due. I set the due date, class time on Monday, just because I thought, well, based on what we discussed, and also if someone wanted to study this a little bit more and being able to do it. Pay attention to these, right? And also mention what analogy you use. Because you can use different analogy, get different circuits, but then the end equations will be similar. This CP has 2 questions at the end of it, which I want you to answer. I didn't set any password because this is online and I assume everyone will be here, which I think most of the students are here. So have a great weekend. I will stay here until 3:55 if you have question. Otherwise, you can go live or we can do some word all together. But I'm gonna stop the recording, okay? Your questions remains private.